Here is a combined summary of the 2 pages. The Appformer framework is a novel mobile application prediction framework that leverages progressive multimodal data fusion and feature extraction. Inspired by transformer-like architectures, Appformer combines a multimodal data progressive fusion module with a sophisticated feature extraction module to process sequential data through self-attention mechanisms. The framework employs points of interest (POI) associated with base stations, optimizing them through comprehensive comparative experiments to identify the most effective clustering method. The refined inputs are seamlessly integrated into the initial phases of cross-modal data fusion, where temporal units are encoded via word embeddings and subsequently merged in later stages. The feature extraction module, employing transformer-like architectures specialized for time series analysis, adeptly distills comprehensive features. It meticulously fine-tunes the outputs from the fusion module, facilitating the extraction of high-caliber, multimodal features, thus guaranteeing a robust and efficient extraction process. Extensive experimental validation confirms Appformer's effectiveness, attaining state-of-the-art SOTA metrics in mobile app usage prediction, thereby signifying a notable progression in this field. The research addresses 3 pivotal challenges in mobile app prediction: accurately representing core data, efficiently integrating multimodal data, and enhancing feature extraction. To address these challenges, the Appformer framework introduces innovative solutions aimed at enhancing the prediction efficiency for mobile application usage. The key contributions include the Appformer framework, multimodal data progressive fusion, and enhanced pre-processing of location and time data. The related work section highlights the correlation analysis between core data and application prediction, mining and expression of core data, fusion of multimodal data, and feature extraction network. It discusses various studies that demonstrate a strong correlation between spatiotemporal information, user information, and application usage. The section also reviews existing methods for word embedding, multimodal data fusion, and feature extraction networks, including co-training algorithms, co-regularization algorithms, marginal consistency algorithms, and multiple kernel learning. Here is a combined summary of pages 3 and 4 of the research paper. The authors introduce a novel framework for predicting application usage, addressing the limitations of existing methods. They identified 3 primary shortcomings: inadequate representation of core data, oversimplified or overly complex data fusion strategies, and limited feature extraction capabilities. To overcome these limitations, the authors propose a new system that leverages rich, interconnected data to enhance predictive accuracy. The problem definition and dataset are presented, featuring a real-world application usage dataset collected from Shanghai, China, during a week-long period in 2016. The dataset consists of various feature data types, including application sequence, user IDs, timestamp sequence, base station IDs, and points of interest (POI) data. The goal is to develop a predictive model capable of precisely predicting the next application a user is likely to use. The mathematical representation of the predictive model is illustrated by equation 1, where a, n plus 1, represents the next application to be used, and x, nm plus 1, n, denotes a multi-dimensional feature sequence incorporating essential historical data required for prediction. The configuration of this sequence is defined in equation 2, which seamlessly integrates app IDs, user IDs, timestamps, base station IDs, and POI vectors. The data preprocessing for app usage prediction is depicted in Figure 2, involving the implementation of word embeddings, clustering techniques for POI data, and encoding of temporal data. The authors employ word embedding techniques to transform the discrete app sequence into a continuous vector space, utilizing the NN embedding algorithm in the PyTorch framework. The specific embedding process is represented by equations 3 and 4, where the embedding matrix is initialized and updated during the training process via backpropagation. The authors then introduce the Appformer framework, which consists of 2 primary components: the multimodal data progressive fusion module and the feature extraction module. The framework is designed to effectively leverage the rich, interconnected data, enhancing predictive accuracy for upcoming application usage. The paper discusses the development of an app usage prediction model, leveraging multimodal data fusion and a novel framework called Appformer. The Appformer framework comprises two core components: the multimodal data progressive fusion module and the feature extraction module. These components are designed to work together, first by progressively integrating data from diverse sources and then by extracting relevant features to enhance the predictive model's accuracy. The multimodal data progressive fusion module is a novel approach that addresses the limitations of existing data fusion methods. It emphasizes context relevance, delineates the importance of data modalities, adopts cross-modal attention mechanisms, and implements progressive fusion strategies. This module cleverly merges encoded app vector, user vector, POI vector, and time vector step by step, preparing the data for the feature extraction module's encoder and decoder. The cross-modal data fusion module, inspired by the decoder module in the transformer, integrates operations such as multi-head cross-modal attention, masked multi-head self-attention, residual connection, and layer normalization, and feed-forward. This module enhances clarity around the computational workflow and is detailed in the provided pseudocode. The feature extraction module, comprising an encoder and decoder, is designed to extract relevant features from the fused data. The encoder processes the fused data, incorporating location and temporal information, and outputs a sequence of vectors. The decoder, utilizing the output from the encoder, predicts the next app usage sequence. The paper also discusses the preprocessing of data, including the use of word embedding for app sequences, user IDs, and time data, and the application of K-modes clustering for POI. The comparative experiments in the paper demonstrate that K-modes achieved the best result among several clustering algorithms tested. Overall, the Appformer framework offers a comprehensive approach to predicting app usage sequences, leveraging multimodal data and novel fusion strategies to enhance predictive performance. Here is a combined summary of pages 7 and 8 of the research paper. The proposed Appformer model integrates a multimodal data progressive fusion module and a feature extraction module to predict mobile app usage. The fusion module combines app, user, POI, and time vectors using linear transformations and cross-modal data fusion modules. The output is then prepared for the encoder input by adding positional encoding. The decoder input is prepared by concatenating the fused POI and app vectors with a zero vector and adding positional encoding. The feature extraction module employs an encoder-decoder architecture, inspired by the transformer architecture, to extract features that reflect complex relationships within the data. The encoder uses multi-head self-attention and feed-forward networks to capture dependencies within the data, while the decoder decodes the high-dimensional representation and combines it with a conditional vector to produce the target sequence. The interaction between the encoder and decoder is facilitated through the cross-modal data fusion module. A comparison of existing data fusion methods for mobile app prediction reveals limitations in their ability to capture complex relationships and adapt to new data types or evolving tasks. The proposed feature extraction module addresses these challenges by adopting an encoder-decoder architecture, introducing attention mechanisms, and designing modular and replaceable feature extraction methods. The cross-modal attention and cross-modal data fusion module are designed to handle multimodal app usage data. The cross-modal attention mechanism uses masked multi-head self-attention and cross-modal data fusion to prioritize important features while reducing noise. A comparison of existing feature extraction methods for mobile app prediction reveals limitations in their ability to handle sequential data, capture deep temporal dependencies, and adapt to new requirements. The proposed Appformer model addresses these challenges by leveraging the enhancements in the feature extraction module, including the encoder-decoder architecture, attention mechanisms, and modular design. This enables the model to capture subtle relationships within the data, adapt to new data types or evolving tasks, and improve predictive performance. The cross-modal data fusion module algorithm is presented, which fuses encoded app vector, A, and POI vector, L. This fusion is crucial for obtaining a richer and more comprehensive feature vector. The algorithm initializes weight matrices for multi-head self-attention and cross-modal attention, followed by a series of operations involving masked multi-head self-attention, cross-modal attention, feed-forward network, and layer normalization. The final output is obtained after another residual connection and layer normalization. The feature extraction module's modularity allows for easy swapping of its components with those from other well-known architectures. Experiments were conducted by replacing corresponding parts of the feature extraction module with modules from Appformer, Appformer, and Appformer. This modular design not only proves the adaptability of the model but also paves the way for future enhancements by incorporating more sophisticated modules as they become available. The evaluation metrics used include hit at K, MRR at K, NDCG at K, and F1 score with a macro setting. Baselines for comparison include traditional machine learning classifiers such as random forest, logistic regression, XGBoost, and various deep learning models like MLP, LSTM, GRU, PCA and LSTM, NAP, App Usage 2-Vec, Deep App, PAULCI, and DUGN. The experimental setup includes model parameter settings, dataset cleaning, and partitioning. The sequence length is set to 4, based on findings from relevant studies. Embedding dimensions for user, time, and app sequences are set to 16, 64, and 12, respectively. The number of cluster centers for POI data clustering is set to 5. The framework configuration includes a model dimension of 128, number of attention heads to 8, dropout rate to 0.05, and feed-forward network dimension to 512. The training regimen involves 20 epochs, a batch size of 128, and an atom optimizer with a learning rate of 0.001. Experiments are implemented on a GPU by PyTorch. 2 different data cleaning and partitioning methods are adopted for comparative experiments, as described in PAULCI and DUGN papers. The PAULCI method is used for subsequent ablation studies and comparative analyses due to its wider adoption in app prediction research. The paper presents a comprehensive comparison of the proposed method with other state-of-the-art methods in mobile app prediction. The results show that the proposed method achieves superior performance across various metrics, including hit rate, MRR, and F1 score. This is attributed to the effective handling and integration of time information, spatial context, and user identifiers, as well as the advancements in feature extraction techniques. An ablation study was conducted to scrutinize the key components of the proposed method. The results indicate that the time encoding and fusion methods, along with the clustering operation of POI data, play significant roles in enhancing the model's effectiveness. A comparative experiment was also conducted to contrast the improved time encoding and fusion methods with the basic time encoding and addition method. The results demonstrate that the proposed method outperforms the basic method across various metrics, indicating its ability to accurately capture the inherent patterns of time information. Furthermore, an ablation experiment was performed on the input to the decoder, revealing that feeding only POI data into the decoder yields optimal results. This is because the user sequence itself consists of repetitive numbers, and the time series changes slowly, making redundant data potentially interfere with the decoder's decoding operation. Additionally, a feature extraction module comparison experiment was conducted by replacing the components in the feature extraction module of the proposed method with equivalent modules from Appformer, Appformer, and Appformer. However, the results did not meet expectations, possibly due to these modules being primarily designed for long sequence prediction tasks and not fully adapting to the characteristics of the short sequence prediction task. Lastly, clustering experiments were performed with different cluster sizes to determine the optimal number of clustering centers. The results suggest that the proposed method achieves the best performance when using 30 clustering centers. The research paper discusses the evaluation of clustering methods for POI data, focusing on determining the optimal number of clusters and testing different clustering algorithms. The authors used various visualization tools and experimental results to demonstrate the effectiveness of the K-modes algorithm in handling noise and maintaining data centrality. The K-modes algorithm outperforms other methods in terms of hit at 1, MRR, and F1 score, indicating its suitability for the task. The study also highlights the limitations of the current approach, including challenges in data fusion, feature extraction, and model updates. The authors suggest directions for future research to improve the model's adaptability and performance. The paper discusses the role of utilitarian and hedonic aspects in the continuance intention to use social mobile apps, and how app popularity prediction can be achieved by incorporating time-varying hierarchical interactions. It also highlights the importance of understanding and prediction of mobile application usage for smartphones, and how this can be achieved through various machine learning techniques such as collaborative filtering, deep learning, and multi-view learning. The authors provide a comprehensive review of various machine learning techniques used for app usage prediction, including supervised and unsupervised learning methods, and discuss the importance of considering multiple views of data in such predictions. They also discuss the role of word embedding techniques for text classification and how they can be used in app usage prediction. The paper also reviews various deep learning models used for app usage prediction, including models based on convolutional neural networks, recurrent neural networks, and transformers. It highlights the importance of considering the temporal and spatial aspects of app usage data and how these can be effectively modeled using deep learning techniques. Furthermore, the authors discuss the role of reinforcement learning in app usage prediction and how it can be used to model the dynamic nature of app usage. They also provide a comprehensive review of various evaluation metrics used for assessing the performance of app usage prediction models and discuss the importance of considering both accuracy and interpretability in such evaluations. Overall, the paper provides a comprehensive overview of the state-of-the-art in app usage prediction, highlighting the importance of considering multiple views of data, leveraging deep learning techniques, and evaluating model performance using appropriate metrics.